Greetings, mathophiles. Welcome to a video in which we'll examine the concept of the instantaneous rate of change of a function, which is sort of a stepping stone in turn to defining the derivative of a function, which we will undertake in a video in the very near future. So we are looking at the graph of a cubic, and it is f of x equals x cubed plus 3x. And we're going to start by taking a look at average rates of change, which ought to be quite familiar to students even of algebra. So I'm going to place a slidable point on the graph, and I'm going to locate it at the point 210. Then I'm going to add another point that I can then slide around. And we can ask ourselves questions like, what is the average rate of change from, I almost had it, from x equals 1 to x equals 2. And of course, that's just a good old-fashioned Algebra 1 rise over run slope. So that's 10 minus 4, which is 6, over 2 minus 1, which is 1, so it's 6. The idea behind an instantaneous rate of change, or at least the way we're going to approach the idea of an instantaneous rate of change, is to imagine ourselves in a situation where we have one fixed value that's of interest, and for that purpose we'll use the point 210, and another that is able to be varied. And so, and I've also added the secant line here to anchor us a little bit in terms of what this relationship is. And as I move this point around that we're considering to be movable, it seems reasonable to imagine that the smaller the x increment, the smaller the horizontal interval, the closer this average rate of change might come to what we could call an instantaneous rate of change. It would be analogous to a situation in which you were looking at velocity over time. And if you had a way of calculating an average rate of change over an interval, it seems reasonable that the smaller and smaller the interval, the closer that would be to what might be reasonable to call an instantaneous rate of change. So if I pull this second point, this movable point, closer and closer to the first one, I find myself in a situation where, let me drag this over so you can see the slope. There it is. We have a situation where the slope of the secant line is about 7. And as I move this movable point around, the closer I get, the closer the x-coordinate of that movable point gets to x equals 2, the closer the slope gets to 7. And of course, if it gets exactly there, we got nothing because we're dividing by 0. But if we're very, very close, it looks as though this slope is in the neighborhood of about 7. A little bit more if I'm to the right, a little bit less if I'm to the left. So it might be a respectable surmise to say that since the average rates of change are close to 7 when these 2 points are very close together, then perhaps the instantaneous rate of change of this function, of its y values with respect to its x values, might be in the neighborhood of 7 when x is equal to 2. We're going to go ahead and formalize that, and then we'll work out an example based on that formalization. So remember the number 7, because we hope to see it again towards the end of the video. Here is the graph of a generic function f, and we're going to explore the notion of how we might formalize a definition of an instantaneous rate of change in the spirit of the discussion we had looking at the Desmo screen. So here is x naught. Here is f of x naught, and we're going to try to answer the question, what is the instantaneous rate of change, or how to define the instantaneous rate of change of f at x equals x naught. Here is some other value x. Here is f of that x. And the average rate of change, the slope of the secant line that connects these 2 points, is f of x minus f of x naught all over x minus x naught. And Based on our discussion, it seems that what we want is for the x to be as close as possible to the x naught. Can't actually get there, of course, because then we would again have a division by 0. There is a object, mathematical object, concept, call it what you will, of a limit that is exactly what we're looking for. The instantaneous rate of change of f at x equals x naught is going to be defined to be the limit as x approaches x naught of f of x minus f of x naught all over x minus x naught. It's just the limit of a good old algebra 1 slope as the one point approaches the other. You sometimes see this written in this fashion. You could think of the x as x naught plus some small value h. This would then be equivalent to the limit as h gets tiny of f of x naught plus h minus f of x naught over x naught plus h minus x naught, which of course is h. So you can use either of these notations. I don't know that it makes much difference, possibly convenience in a given situation, but they're conceptually equivalent and they're functionally not too dissimilar. Now let's take a look at a specific example that harkens back to what we saw on the Desmos screen. In this example, we'll use the same function we saw on the Desmos screen, and that was f of x equals x squared plus 3x. And we'll ask essentially the same question that we were exploring, which is what would be the instantaneous rate of change of this function f at x equals 2, only now we'll approach it formally by means of the definition that we just gave. So we want the instantaneous rate of change. People are probably going to know what this abbreviation means if they know the context is calculus, otherwise possibly not. But we want the instantaneous rate of change of f at x equals 2. This is going to be, according to our definition, the limit as x approaches 2 of f of x minus f of 2 all over x minus 2. What is f of x? It is x squared plus 3x. What is f of 2? Well, if I stick a 2 up in there, I get 4 plus 6, which feels like 10. And our denominator is x minus 2. Now, the bad news is, in these contexts, you will always have a 0 denominator, which presents challenge when you're evaluating limits. The good news is, at least if your numerator is a polynomial, then under reasonable circumstances, under circumstances in which you're likely to find yourself, the numerator is approaching 0 as well, which means that the denominator should be a factor of the numerator, according to the factor theorem. So I'm going to proceed on that basis. This is limit x approaches 2, x minus 2 times x plus 5 all over x minus 2. Now, if x were equal to 2, we would be in trouble because nothing here would be defined. But when we talk about the limit as x approaches 2, we're talking not about values at 2, but values near 2. And in that case, it's perfectly legitimate to reduce the fraction. And if I plug a 2 in here, I get 7. And 7, as you may recall, was the number I asked you to remember at the beginning when we were exploring this numerically. I hope this has served as a good brief introduction to instantaneous rates of change. Happy mathing.